Travis Collins, talking about gr-doa, an out-of-tree module for direction finding. Hopefully we can get the laptop set up immediately. Is your demo in the expo booth? Is it running in the expo booth? So that was more of a rhetorical question. You just could have said yes, because I think it is. If you go to the Edis booth, you'll actually see Travis's code, but you don't actually know yet what he's talking about. So let's give you some time. Did you plug in your laptop already? Because it's not showing up yet. Perfect.
Yeah. All right.
Okay, Travis, take it away.
It's a miracle that worked. All right. Okay. So first of all, how many have heard of gr-doa? Just out of curiosity. And if you're from Edis, you don't count. So it was a project that I worked on with a colleague of mine, Shrikant, while I was doing my PhD, and he was doing his postdoc. And it was actually sponsored by Edis at the time, out of some a prototype that I built using a series of N210s. So I got my PhD at WPI, and the lab I worked out of was the Wireless Innovation Laboratory. And a lot of this work was actually sponsored by the NSF as well. I got to mention Analog Devices, who I actually work for now, and paid for me to come here. So, you got to pay homage. So we'll talk a little bit about the project background, because the repository is more of like a formalization of some work that I did while I was doing my PhD, and some other hardware options that you can run the code on, because it's primarily designed for the 200X, but you can use it with N210s as well, which was my original design, and an FMCOM5 board. And then I'll move on to some antenna calibration and how we actually do that, and some testing, and if we have time, some of the more researchy type stuff that we use beyond what's available in the repo now. So the project was kind of born out of a project I was working on called the Wi-Fi US project, which actually stands for, I believe, Wireless Innovation with Finland and the US, which I think is a terrible name and kind of just sounds like we're putting up routers across the country. But what the project was doing was we were trying to set up a localization testbed to replace a really analytical model that our friends at Tampere University had developed. But we needed to generate a baseline system which was based on music and which is basically the gr-doa out-of-tree module. And once we got that running and proved that you could get good results, we moved on to a more advanced signal processing technique based on something called EADF. So there are a lot of direction finding algorithms out there. The ones we use, I would say, are the most popular, which are music and root music, which are under the noise subspace type algorithms. And the one we developed for, the one we implemented for our research was called FFT EADF. But we might add some more someday, but right now I'm kind of busy, so these are what's in there now. So the basics kind of behind phase array direction finding is that you have a signal coming from the far field. So it's planar, and you want to figure out, based off of the delay that each of the receive elements that you have produce for that signal, how you can relate that to a direction of that source signal. So the signal has to be in the far field. Your antennas have to have a fixed and known phase, ideally 0 phase offset between them. The antenna positions have to be known, and the signal has to have limited correlation between the elements. So in the repository right now, we only implement uniform linear arrays, and you can mathematically relate them using like a signal sieve cascade K that we have here, and the array manifold V, which we'll use to represent the mapping between the phase of the input signal and the position of the antenna elements. So Musicworx, it's a subspace-based algorithm. So we have our receive signal model X here, which can be made up of at most big D signals, and D has to be bigger than, or excuse me, the number of elements that you have has to be bigger than the amount of received signals. So by taking our received vector X and autocorrelating it and taking the eigendecomposition of that, looking for the nulls will tell you the direction of the signal that it comes from. So we usually invert this and look for the peaks. So you can think of how Musicworx as basically a spatial filter, and you're looking for the most correlated areas of the antenna response. And here in the plot is something called the P spectrum, or the music spectrum, as people call it, which the peaks represent the source angles, the source positions of the emitting transmitters. And as you increase the number of transmitters, the sharpness of the music spectrum gets better. Ideally, that's not always been the case in our testing. But the more elements you have, the more receivers that you have, generally the better you'll do. So if we look at the CRLB of music, which is derived in '89 by Stoik, we noticed that it's pretty robust. At 0 SNR, you have an RMSE of less than 1 or under 2 degrees, which is pretty good, right? But you'll notice, since this is to represent a uniform linear array, that on the ends of the perspective, you have asymptotes. So you can't measure, or as your signal moves towards these positions relative to your array. So if I have a set of antennas, as the target moves to the corners of the elements, so the extremes of the perspective, then I can't, my estimation gets worse and worse. So music is parameterized by a snapshot length, which we call L, and as it gets bigger, you're basically averaging more and more data, and you'll perform better to a point. So we translated this math into a set of blocks. Autocorrelate, which is mathematically the simplest thing that we're doing, is actually the most computational intensive, just because it consumes a ton of data, because it's a matrix multiply. So we typically run with a snapshot length of 1024 or 512, or even bigger here. But this block consumes a lot of computational power. So the blocks under the hood are actually implemented using a library called Armadillo. I'm not sure if you're familiar with it, but it's a C++ templating library to do linear algebra. And it has a lot of the really useful functions like eigendecomposition, and makes use of like BLAST libraries or Intel kernels that take use of SIMD operations. So you can get good speed advantages using Armadillo. So we've implemented root music and music itself just for linear arrays in the repository. And we have some GUI tools as well, including a compass that's really specific to gr-doa. And we provide a real-time P spectrum from the music block itself. So root music just spits out a number, and you can plug that into one of the compasses to give you an angle. Now, so this is a picture of our original design that we have. So our lab had or still has a ton of USRPs. I think we have 14 N210s. So the array fixture that we built here assumes they are operating at 2.4. So you have a spacing of lambda over 2, which is the sweet spot for antennas, or for linear arrays. And it's super important, actually, to have same length cables between everything. So we didn't use match length cables, mainly because we had already spent like $700 on the octo clock, and asking my advisor for $2,000 for cables wasn't really going to fly anywhere. But the performance that we had was still pretty good. So the setup utilized 4 N210s for receive, and we actually have a fifth in there to provide additional calibration. So the octo clock will provide sample time alignment, and it will provide frequency alignment. But the problem with the N210s is that you're not phase aligned. So you have to fix this. And so the input signals will have a random phase associated with them. And if you set up your blocks to run with time commands, this phase will be repeated. So when you restart your flow graph, power down the radios, the phase offset will remain the same between the chains. And this is assuming that I believe you have to use the SPX boards to only do this, but you can talk to the Edis guys and they'll let you know. So the way we went around fixing this was we would take a secondary tone and feed it into the transmit chain of each board. And then that would actually bleed over into the receive chain, and you would measure that. Which is, like, it worked for us. It actually worked pretty well for us. And it prevented us from having to actually disconnect cables and move things around constantly, which would actually, when you move the cables around, we found that it made the phase change over time. So this setup, we actually have the blocks. They're actually not published for N210, but if you want to talk to me afterwards, I can show you how to get this up and running. And this will work if you don't have SPX boards. I think we had a bunch of XCVRs that we were using at the time. And we essentially measure the phase difference between all the channels, and then we correct it all in software. Now, so the problem with music and a lot of the phase array direction finding is that it's really sensitive to reflections in the environment. And our lab has like metal walls, which is really bad. And it's like all cubicles, so it's almost impossible to get clean signals. So what we ended up doing is going down to the hallways in our building. And the first day I was actually setting up, like Crimson Key was coming by and giving a tour, and they were all super interested. Like, what is this? And I said that we were studying the outcomes of cancer from RF energy on humans or something like that. Yeah, no one walked down that hallway for the next hour, which actually worked out great for me. So we actually ended up showing this off at New SDR, which is a conference in New England or in Boston, or actually it kind of hops around the cities in Boston or in Massachusetts. We talked to the Edis guys, and they said they were coming out with the new TwinRx boards. We got beta versions of them at the time, and we implemented our music algorithms with that hardware. So in gr-doa, we have a custom wrapper around the UHD block that will set up the UHD source in a way that provides repeatable phase offset between the channels. So the twin RXs have the same problem where the phase is different between all chains, but it will remain constant. But the drift on the twin RXs is a lot better from what we saw in our results. So once they've been running for a while and stabilized over temperature, we're very happy with them. So another option is the FMCOMS5 board, which is a 4x4 radio. So this is just a Xilinx board right here. I believe it's a ZC102. But this is the FMCOMS5. And I always love looking at this board because it just has so many SMA connectors. It's kind of ridiculous. But it's so this is actually self-phase calibrating. So you don't have to fix the additional phase offset that's associated with some of the USERT boards. But it's basically a dual 9361 board. So you have 64 megahertz or 61.44 megahertz of bandwidth on this device. So what we've been trying to do is eliminate as much of the physical outliers as we could, because at the end of the day, direction finding is really a physics problem. So we wanted to limit as much as we could the drift between the radios over time, and the twin RX really did that for us. Positioning error is, so we have kind of an interesting solution to that, which I'm going to talk about. And we actually provide antenna gain and phase mismatch calibration in the repository as well. And to deal with reflections, we moved away from the hallway and into a real anechoic chamber. And we actually couldn't fit the original like cart array into the chamber. So it was great when we got the twin RXs because they actually fit. And there could always be bugs actually in your software. So if you think your software's perfect, then yeah, you're not. You're wrong. So if we think about actually the element positionings, so you're never going to be perfect. Even if you place them the best that you could, there's always going to be some error associated with the actual positions of the antennas and where they sit. So if we just add a little bit of noise to our manifold vector, which affects our positioning, we can see that as we scale up this error, it can produce as much as 3 degrees of RMSE. And to reduce this as much as we could, we actually went out to Home Depot and we bought a bunch of pegboards, which was the best like $10 I think we spent on the project because it allowed us to really precisely place our antennas, including like the targets and all the array elements. So ironically, the pegboard actually had a data sheet, which I found, and told me the tolerance of the holes, which is about 1/8 of an inch. So that gives you about 0.7 degrees of RMSE in worst case. So as I mentioned, we actually include antenna calibration in gr-doa as well. And this is kind of built upon music estimation inherently. From a paper called From Soon in 1994. But basically, we place a transmitter at a known position, and we make an estimate based off of that transmitter, and then we correct that estimate, or we provide the difference of that estimate to an additional block that we have that will fix the gains of the individual elements. So there are a lot of ways to actually do this. This is kind of the simplest we found. You can actually, there are implementations that have you place like many elements, and you'll do better in that case. But we only have so many radios, so that becomes more and more difficult. Now, for convenience, we provide flow graphs that actually show you how to calibrate the phase between the individual chains. And we provide a flow graph that will allow you to calibrate the antennas. So we're trying to remove all of the low-hanging fruit that we can to make your direction finding as accurate as possible. Because not everything can be fixed in software. If one of your receive chains is out of phase, how do you know that? How do you compensate for that? So this is more of dealing with the physics problems associated with direction finding. So the testing that we did was in a relatively small anechoic chamber, but we placed elements along, or excuse me, we placed targets along azimuth as best as we could. So since it's a uniform linear array, we don't really care about elevation. All we care about is azimuth. And of course, we used a dual twin RX setup, so we have 4 receive antennas. And we provide measurements. We did measurements with music itself and root music, just for comparison. So this plot shows the RMSD error for the estimate across azimuth, with and without calibration. So music and root music match identically, which they should. And there's almost no variance in the data that we had, so that's why I didn't put error bars in these measurements. But there's actually a huge dramatic change when you turn on antenna calibration, or when you do an estimate. And if you look at the P spectrum, you have a huge SNR gain in it as well. And you'll see that there's actually a change of the peak position with and without calibration. Okay, so let's go to a little demo here. So the repository contains a ton of actually octave code that will show you, that will walk you through all the root music algorithms, music algorithm, antenna calibration. We have tons of test code for all the blocks, which I know Jonathan was kind of griping about yesterday. But in the repository, there are actually just simulation-only examples too as well. So here's an example that has 2 targets. So we have a source at, let's see, you can just run it. So at 123 degrees and 30 degrees. And you can see as I move the sliders, the P spectrum changes. And those lines are actually not an artifact of the music algorithm. They're a problem with the scope itself. We've verified this a number of times.
Is there a bug before?
Not yet. Not from me yet. So these are the compasses too, as well, and they track as you change the source angles. So if you're teaching direction finding in your classroom, this is like a good place to start. Or if you're getting up on direction finding yourself, and you don't have thousands of dollars to blow on an array, this might be a useful starting point. Okay, so let's see. So as I mentioned, we provide hardware-specific flow graphs in the repository that include phase estimation and antenna calibration and simulations. And a great place to actually start is the octave code that exists there, because it actually runs through the algorithms themselves. And we actually have a white paper too in the repo. Now, kind of switching gears a little bit to the research aspect of this. So once we knew that music was working and our array processing was accurate, we could move on to the more interesting aspects, or the more research-oriented aspects. And this involves a technique called effective aperture distribution functions, which is basically it was implemented actually to do designs of antennas, where you take an antenna array in an anechoic chamber, and you measure the spherical response of it, and then you take a Fourier transform to put it into an alternative representation. And this is actually really nice because since you're going through the Fourier transform, the result is smooth, and the Cronauer lower bounds are easy to calculate, which isn't really always true. Like even if you, for a, say, a spherical representation of an antenna response. Like if you look at a, say, a monopole, it'll look like a donut, right? But in the top will be actually really hard to differentiate. So finding the Cronauer lower bounds can be difficult. And if you have a really funky looking antenna, this gets even harder. So this process works by taking the spherical response, B, negating it, and stacking it. So you get it to repeat in azimuth and in elevation, your measurements. And you take the FFT of that, and we use these mapping vectors to create a polarimetric array response. So we don't have the equipment to actually do this for an antenna. So what we did was that we took one of our monopoles and took the data sheet and said, okay, it's relatively round, and let's create a simulation that gives us the response of this antenna, and let's generate the EADF response, which you can see on the right. So the one thing you'll notice is that it's just basically there's a hump in the middle, and that means that all the information or all the detail in the response is located there. So you can remove the outer columns of the response matrix and get the same accuracy in the response. So with this, you can actually do DOA estimation with taking a channel estimate, convolving it with these, multiplying it by these polarimetric responses, taking the inverse Fourier transform, and then searching over that surface for peaks, and that will give you the direction of a source. And we implemented this using an OFDM link based off of some of the OFDM code that exists in GR right now. And we modified it so it could do SIMO reception, so it will actually expand it as many receive channels as you want, and as long as they're phase aligned at the, or the channels are assumed phase aligned at the source, then this will actually give you a channel estimate and tell you the relative differences in the paths. So we implemented this all in GR, and it actually compared relatively well to music. So basically on par, which was we were expecting. But the usefulness of EADF is that if you can get a really accurate polarimetric response, then you can do even better because you have the exact gain or response of that antenna. You're not just using kind of like an arbitrary model for doing your correlation. So if you want to look at the code, it's up on Edis's GitHub page. And there's actually a really nice white paper that we put together that kind of actually goes over a lot of this presentation, or the first half of it, and discusses the different techniques that we use in the blocks that we have. Okay. All right. Thank you.
All right. Plenty of time for questions as before. Marcus?
So did I get it correctly that you basically can calibrate your antenna array as the array it actually is? And then you do what with that data? Do you multiply that to the auto/cross correlation matrices, or?
For the second implementation that we had?
Yeah.
Yeah, so we take a channel estimate based off of the paths. So when we recover the signal, we estimate one chain. So all of the correction that you do is on that chain. So you maintain all the phase differences associated with the direction. So we take that estimate, and then we correlate it with the response to the antenna. And that will tell you the most likely direction that the signal's coming from.
Okay.
Questions?
Yeah.
Oh.
So You're doing root music with a single target, or is this a
So you can, so as long as the number of targets is less than the number of elements, it's been simulated up to that point.
Okay, yeah, makes sense.
Yeah, so yeah, the weakness of root music is that assumes you have, or the basic implementation assumes that you have a linear array. So there are versions that work on arbitrary arrays.
So that would lead me to why don't you do Esprit? Because like, I mean, you basically know the dimensionality of your problem and you know how many peaks you're expecting, so.
Yeah, so I don't really know the details of Esprit, but it's, so the inherent problem with music is you need to know the number of sources, right? So, which is, or it's the problem with root music. So if, there are ways to do direction finding where you don't know them.
Yeah.
But yeah, it's a little bit more advanced.
Thanks.
Anyone else?
Okay.
Oh, there we are.
Are there any plans to expand this to a nonlinear or non-uniform array, or even a two-dimensional array for direction finding?
Yeah, so can you raise up your hand just so I can see? Okay, there you are. All right. So we actually do have blocks for circular and planar arrays. They're just not published.
Okay.
But they're done. They actually have QA code and simulations. So, yeah.
Do they go both azimuth and elevation for your planar? Okay.
Mm-hmm.
Excellent. Excellent.
Yeah. So the response, you can't use the vector scope for it because you have a two-dimensional. So I don't know how we would view that.
There's a matrix plot. You could use that, maybe. No.
Okay, or maybe, yeah.
It would be slightly unintuitive. But, like, I didn't want to interrupt anyone else if they have. No? Okay, looks like Michelle wants to say something before we head out.
Hi, everybody. We have a whole new category in the CTF. It's an amateur radio category. It has two different types of challenges. One is pretty hard, we think, and it's on 146.520. If you want a transmission to capture, it's an intercept challenge, then just let me know, and I'll fire off one whenever I walk by that particular radio. And we have a donated challenge from Clayton Smith, and this is a whole set of challenges under the amateur radio category, so check it out and give it a shot. They range from pretty easy all the way up to hard. Hard meaning you have to transmit and you have to do some coding. So that's the update on the content. Update on the scoring, there's 50 teams registered now. 44 are on the board. Wayland Yutani is in the lead. Unconfined_U is right behind in second place. Argyle Sox, or Argilo, is third. And we have our first negative point scoring team.
Oh shit, I should present.
Yes, we have a new black ribbon. It is Spam and Eggs at -10. Good job, Spam and Eggs. Keep it up. Good luck, everybody, and let me know if you have any trouble, have any questions, want to learn anything, have a challenge or a prank. And the unplanned hack with the wireless mic was actually one of our teams. So.
Excellent. So before we wrap it up for this session, there is a coffee break now. We'll start again at 3:45 sharp, and in parallel to the 3:45 presentation, there will be another tutorial on the digital comms, and then after that, there is Michael Osman's introduction to complex numbers. They're both in the shell room, of course. So 3:45 sharp, we'll start here again. See you guys later, and coffee is down at the expo hall.